It's time for us to talk about some very, very common different types of sequences and series that are very specific and useful later on in math. We're going to talk about arithmetic sequences and then series, geometric sequences and then series in the next 4 videos, this video and 3 more. So we're going to start with arithmetic sequences, something that's very useful, very common. In fact, you're going to see that we can talk about some sequences we've already defined in a different way, and it's much, much easier. So here's what an arithmetic sequence does. It's a sequence where the difference between any two sequential terms is constant. Now, here's what that means in plain speak. You're adding the same number over and over and over again. So you're like adding 3, 3, 3, 3. You're adding that to every single term. Now, what's it going to take to do that? You need to start with some number that's given. And then you need to know what number you're adding over and over and over and over and over again. Well, that number that you're adding, it's called the common difference. Why is it called the common difference? Why do they define it that way? Because if you take any two terms that are right next to each other and you subtract them, it's going to give you the same number over and over again. That is the number that you're adding to get from term to term. Let's take a look at one right now. So if I went from 2 to 4 to 10 to 14 to 18, can you identify where we start? What's the value of the very first term? 2. You need to start somewhere with an arithmetic sequence. You have to start somewhere, like 2. And then you need to be able to tell what you're adding to get to the next term, and it's got to be the same every term. So take a look at this. If I take any two sequential terms, that's 2 and 6, or 6 and 10, or 10 and 14, or 14 and 18, and I subtract them. 6 minus 2 is 4, 10 minus 6 is 4, 14 minus 10 is 4, and 18 minus 14 is 4. The number I'm adding over and over and over and over again is called the common difference, and in this case, it's 4. This is how arithmetic sequences work and how they're structured. Why are they called arithmetic? It sounds kind of like arithmetic, and arithmetic means adding. It's exactly right. So we emphasize the wrong syllable when we say arithmetic instead of arithmetic, but it's the same idea. You're just adding the same number over and over again. In this case, we start at 2, we're adding 4. You could find out any other term in here if you continue the sequence. You know it's going to be 22, then 26, and then 30, and blah, 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 blah. You can do this forever and ever. Now, that's great, and that defines a sequence for us recursively, which we've talked about briefly, and I'll do it again right here when we talk about odd numbers. It will define a sequence recursively for us. That's not quite what we're looking for. We want to be able to find out any term that we want. Like I want to be able to find the 100th term and not have to do a whole lot of work to it. So here's how we can do that with arithmetic sequences. They can always be written as a sub n equals a sub 1. What is that? Well, that's the first term. You do need a starting spot for arithmetic sequences to be structured appropriately. You need to know where you start. So find your first term. It should be like 2 or 1, that's that example. And then n minus 1 times d. Now, why n minus 1 times d? If d is the common difference, d is what you're adding to get from term to term, well, what do I want to be able to do to get to my 100th term? Now, get this. If I want to get to my 100th term, and I know I start at, let's say, 2, if I want to get to my 100th term and I start at 2, 2 burns up one of the terms. There are 99 terms to get to that 100th term, so I would add 99 common differences, not 100 common differences. I got 99 differences, but the first term ain't 1. All right, you've burned up that first term. You've called it 2. You're going to add 99 common differences, in this case 4, to get to that 100th term. So if they're always structured that way, I hope that makes sense to you. I hope you see, like, if this is the way that arithmetic sequences work, your first term counts, right? That counts as one term. How do you get to the 100th? Add 99 common differences to get to that 100th. If we want to write any arithmetic sequence and we can define it this way, it's really easy to do. All you need is the first term and the common difference. That's 4, and then we can structure appropriately. So our arithmetic sequence is structured as, let's see, a sub 1, that's my first term, 2, plus n minus 1. Why n minus 1 again? N minus 1 is not the same thing as n because this is your first term. It counts as something. So if I'm going to add up a whole bunch of common differences, how I get from term to term, check it out. How would I get to the third term? Third term. I would add 4 how many times? Well, I'd add it once, then twice. That's 1 less. Why is it 1 less? Because this counted as one of your terms. You didn't add 4 to get here. You started at 2. That counts as one of your terms. Therefore, it takes 1 away from whatever index you want to end at. That's what happens. Now that's it. I mean, that is arithmetic sequence. It really is that easy. Identify where you start, identify what you're adding or the common difference, take 2 terms, subtract them. Identify that it actually does work here. So 4, 4, 4, 4, 4, it's going to be adding 4. And then simplify it. Because this distributes, gives you 4n minus 4, we would get 4n minus 2. This will give you the terms of this sequence, which is very nice. If I wanted to find the 100th term right now, I wouldn't have to do what is that, 95 more terms? I would just plug in 100. The 100th term is 4 times 100 minus 2. That's going to be, let's see, 400 minus 2 is 398. The 100th term in this sequence is 398. Now get this, please do not confuse this with series. These are not series. We have not added this up. We will talk about how to do that, but this is not it, okay? This is just the 398th term. It's not adding up the first 100 terms. That would have to need summation notation. This is not what we're doing, or to show that this is a sum somehow. This is just the 100th term here. And if you want to write this out, you could do it. You could add 4 a whole bunch of times, and you would eventually get to 398. I hope that makes sense. I hope you're seeing the idea of you're taking 4 and you're adding it over and over again. But if you want to end at the, let's say, 100th term, you need to add 99 4s, not 100, because that counts as your first term. There's 99 more to go. That's what's going on. Now, do you have to simplify from here to here? You really should. You should also look at the fact that this common difference becomes not a slope, although it is linear. It's going to increase at the same rate. But your coefficient of your nth, your index, I would say. So that is where your common difference can be found also, which is kind of fascinating. Not too bad. There's really not much more I can explain about this besides identify your first term, your common difference, and you can simplify what you get out of that. Let's look at the next one. If you remember from our sequence video, we defined odd numbers, 1, 3, 5, 7, 9, as a sequence. We did it 2 different ways. The first way we did it was we made 1, 3, 5, 7, 9 as terms. We related it and got the terms of our sequence should be given by 2n minus 1. Just like this, if I wanted to find the third term, I should be able to plug in 3. Well, 4 times 3 is 12, minus 2 is 10. That should work. This also works. If I want to find the 5th term, I'd plug in 5. 2 times 5 is 10, minus 1 is 9. That actually does work. But it took us a lot of effort to actually get there, if you remember. If we know that this is an arithmetic sequence, this is a lot easier. So I don't know if you remember that from our sequence video, but it took us some time. It was kind of a headache because we had to relate it back to even numbers and subtract 1. If we understand this is arithmetic sequence, we understand that, oh, look at this. My first term is 1. I'm adding the same number over and over and over again. 1 plus 2 plus 2 plus 2 plus 2, or take any 2 numbers and subtract. 3 minus 1 is 2, 5 minus 3 is 2, 7 minus 5 is 2, 9 minus 7 is 2. That's a common difference. I'm adding 2 over and over and over. Well, if we have a first term and we can identify a common difference, it is arithmetic. We get first term plus n minus 1 times common difference. Common difference here is 2. That is a whole lot less work than what we did with sequences. So if we can and this is the point, if we can identify that something is a specific type of sequence or series, it becomes a lot more predictable. We have a lot more formulas for it and it becomes easier. So that's a very important concept to understand, is we want to try to classify stuff. When you get into Calculus 2, you're going to try to classify this as what type of test is going to show me convergence or divergence of this particular series. And then we can use that on stuff like, we can use that. It's really important that we're able to identify stuff. If we can identify arithmetic, look how much work it saves us. Way more work than how we did that with sequences. The other thing that we did, and I want to refresh it because I didn't really go over it very much, but the other thing we did is we defined stuff recursively. So can you take and define recursively? What recursively means is based on the previous term. So for instance, if I can define my first term as 1, can I say what my second term is? My second term would be my first term plus 2. My third term, so notice that, my second term is my first term plus 2. My third term would be my second term plus 2. My third term is my second term plus 2. We can deal with recursive formulas by basing them on previous terms. You would just need to know what your starting point is and then a formula to get to your next term. That's what recursive means. It's very similar actually to this, except that it doesn't wrap everything up in a nice little package. It says in order to find your 100th term, you would have to know your 99th. You'd have to know all the terms before it. That's what recursive does. So this is a way to define a recursive formula. You basically get a first term and how you find your next term. Notice that it does work. This says start at 1. I have 1. What's your next term? Okay, if I wanted to find a sub 2, I would look at a sub 1 plus 2. Since a sub 1 is 1, that would give me 3. What if I wanted to find a sub 3? Or how about a sub 5, maybe? If I want to find a sub 5, I would need to know the fourth term because it says take a look at your previous term and then add 1. My fourth term was 7. 7 plus 2 gives me my fifth term of 9. That's how recursion works. It's looking at the previous terms and doing some manipulation to get that next term. So hopefully that makes a little bit of sense as far as a recursive formula goes. I just wanted to illustrate it here. You do deal with it occasionally. So what we're going to do now is we're going to come back with one example about kind of a manipulation. What if you're given a couple terms? Can you figure out a formula from it? So we'll talk about that. Okay, last example, very, very common one. You see this a lot of homework, a lot of tests. A lot of people like to ask this question. So if you have an arithmetic sequence, they're giving you 2 terms. Can you find out the formula and then use that formula, of course, to find out any term that you want? Yeah, of course. Otherwise, we wouldn't be doing this. If I've said, nope, then we're done. Video ends. That'd be kind of funny. I'm going to do that someday. But yeah, of course we can do this. I'm going to show you exactly how to do that. One thing to notice here is that if the 8th term is 75 and the 20th term is 39, can you have an arithmetic sequence that is decreasing? Sure, you're just adding a negative number. That would be subtracting. Your common difference would be negative, and in this case, we're going to get that. Here's the idea behind doing this. If you have 2 terms that are given, then what we're going to do is we're going to create a system of equations based on those 2 terms. So we're going to write out what those terms are, use the things that are missing, which is the first term and the common difference. You don't know what the first term is here. You don't know what the common difference is here. If you did, you wouldn't have to do this problem. It'd be kind of nice. But we don't know those 2 things. That's 2 unknowns. We need 2 terms to create 2 equations to solve our 2 unknowns. That's how systems of equations work. We're just starting to delve into that right now. We'll deal much more with systems of equations after we do trigonometry. So here's what we know. We know that the 8th term, that's a sub 8. We know that the 8th term is 75. 8th term equals 75. Well, let's do 2 things with that. Let's fill out as much of this as we can. Now, we don't know the first term, but we do know that n is 8. And we don't know d, but we do know that the 8th term, this represents the 8th term, is 75. This is one equation with 2 unknowns that represents half of our system. The other thing we know that the 20th term is 39. Now, we still don't know the first term, but we do know that the 20th term would have an n of 20. We still don't know the common difference, but we do know that this represents the 20th term, and it's equal to 39. I hope that you see the utility in knowing how to solve a system of equations. This is one equation with two unknowns, another equation with the same two unknowns. We can use the two equations to solve for the two unknowns. This just helped us set up. So what we're going to do is we're going to take a look at this part of it, just this, and treat that like our system. So we're going to simplify a little bit. So a sub 1 plus 8, or 7d, that's 8 minus 1, d, that's 7, 20 minus 1 is 19. And then we're going to find some opposite terms. That's how solving systems works, is you find some opposite terms when you have two variables in two equations. These would be pretty hard to get to be opposite terms. These are pretty easy. So choose one of them and multiply by -1, thereby getting opposite terms. I'm going to choose the top one because I feel like it. It's really convenient, isn't it? That since both of these formulas are always going to have a sub 1, you just multiply one of them by -1 and you automatically get opposite terms. So that does change the sign of everything though. So negative a sub 1 minus 7d minus 70, or negative 75. Now we can add that system. Negative a sub 1 plus a sub 1 is 0. Minus 7d plus 19d is 12d. And negative 75 plus 39, 36, negative 36. So when we divide, negative 36 divided by 12 is negative 3. It's okay to have a negative common difference. It just means that you are subtracting 3. And if you did this, if you started with 75 and you subtracted 3 12 times, you're going to get 39. Now, just like every other system of equations ever, you can solve for one variable, but you have to plug it in somewhere to solve for the other one. So we've just found the common difference. We know it's negative 3, but we need a starting term, an a sub 1 to figure out what our formula is, and then we're going to use this to plug in. And that's going to be very simple, but we need to find that a sub 1. So use either one of these. I'm going to use this top equation. I'm going to plug in negative 3, because I don't want to multiply 19 times negative 3. And then I'm going to subtract it from 75. So 7 times negative 3 is negative 21. If I add that to both sides, we get positive 96. That should make sense. If I'm subtracting 3, then my first term should be more than that, because I'm subtracting 3 7 times in order to get there. So our first term is 96. By the time we get to our 8th term, we'll have subtracted 3 7 times, not 8 times. That's our starting term. It takes up one of those terms. I'd subtract 7 times negative 3 to get to our 8th term, and we would get 75 out of that. So now we're going to take this information. We have our first term, we have our d. We now can fill out that formula. So our sequence is our first term plus n minus 1 times our common difference of negative 3, which we've already found. Let's go ahead and distribute. So distributing, that's minus 3n plus 3. Writing this a little bit differently, you can leave it like this, is totally fine. Negative 3n plus 99. This is probably more appropriate. It doesn't matter which one, but let's check a couple of these. Let's make sure this actually works. Let's plug in 8. If we plugged in 8, that's negative 24. 99 minus 24, this will probably be easier to see. 99 minus 24, that's going to be, let's see, 75. Oh, hey, that works. This one's also going to work if I plug in 20. So plugging in 20 here, 3 times 20 is 60. 99 minus 60 is 39. That works. Now, can we use it to find a 12th term? Yeah, easily. All we have to do is plug in 12. Either one will do it. Plug in 12 here, you're still going to get 36 or negative 36. So 99 minus 36. 99 minus 36 is 63. That's a bit easier than subtracting 3 another 4 times from 75. But if you did it, if you subtracted 3 4 times, that's subtracting 12, you would get, let's see, minus 12, that'd be 63. And that's exactly what we get there. So either way you want to go, but this is definitely easier if you don't have something very close to a term that's given. I hope it made sense. I hope you see the utility in having the system of equations. It's not all that bad, but you do need to know how to structure it. Otherwise, it can be very confusing. You go, I don't know where to start. Create for yourself a system. And then we can find the starting term, a sub 1, common difference, d, and put it back together. Simplify just a little bit, and then you're done. So hopefully I've made arithmetic sequences make sense to you. Next, we'll talk about arithmetic series, and then we'll move on to geometric sequences and series. Have a great day.